This is a circle. What direction does this circle point? Hmm? What direction does any circle point? This is another circle, isn't it? Ooh. What direction does a circle point? The way you answer that is to ask yourself, well, gosh, what is the one direction this circle isn't pointing? What that means is this. This circle obviously is just a shape that I can draw in an X, Y plane, isn't it? I can just draw a circle on a plane that's made of an X and a Y. The one direction that isn't is the Z. See? So, when I ask you what's the one direction a circle points, the answer is the one dimension that that circle isn't in. It points perpendicularly to itself. It points perpendicularly to its face or to its opening, whatever you care to use to word it. So what I want you to realize or remember is even though a circle is pointing in 360 different directions, isn't it? The one direction it isn't pointing is straight out of or straight into. All right? Hmm? Hmm? Now, the reason I bring this up is I will show you a little more. We've been talking about Tony, haven't we? Huh? This is a golf ball. I'll be awaiting my royalty check from Callaway. Um, that golf ball is going in circles, isn't it? If it's going in circles, it has Tony. It's got Romo, right? And if I were to ask you what direction is that circle, you'd say, gosh, I don't know. It's going this way, isn't it? You would draw just a circle and you'd say, I don't know, the sucker was going in that way. What direction is its mo? But the mo is always changing its direction, isn't it? It's all, I mean, up here it's that way, over here it's that way, here it's that way. The mo, linear mo, is always changing, isn't it? But its Romo isn't. And you guys also know that, hey, this has Mo. This is, from our perspective, a counterclockwise rotation. And that's obviously different from going in circles that way. That's a counterclockwise rotation. So those two will have different amounts or different directions, or I should say directions, worth of Mo. All right? Because you guys all know, just as a review, Mo, linear Mo. All right? Linear Mo. It's a vector. It's mass times velocity, and that velocity is a vector. Therefore, momentum is a vector. It's in whatever direction the velocity is, right? You guys all also know that V's become omegas, right? So if V is a vector, well, gosh, omega is a vector also, a rotational velocity. That's why we use the word velocity for it. So if this guy was going in circles in a CCW fashion, well, we have to somehow come up with a sign that means CCW. And a way that we end up doing that, as you remember, counterclockwise we said is a positive torque, right? And that's going to end up being positive for this because the way you figure out the direction of this golf ball's Tony is to use, again, it's called a right hand rule. You use your right hand. Hopefully you can tell this is my right hand on the video here. Okay? take your fingers and curl them in the direction that that golf ball or whatever item is rotating. All right, and you can see the arrows are still there, right? They're rotating this way counterclockwise. So I'm going to curl my fingers counterclockwise. My thumb happens to be in the perpendicular orientation of my fingers, isn't it? My thumb and fingers are perpendicular to each other, right? So if this is going that way, then this item's toning, its momentum is literally out of the page. It's coming straight out of. All right, so that's positive in the Z, isn't it? Something that's straight out of, in a Y, positive is upwards. That's positive Y. To the right is positive X. You know that. Well, for Z's, a positive is outa, which is a circle with a dot. So the L, remember L is mo, is out of the page in this example if you're going CCW. Okay, that's how you keep track of the direction of the momentum. Now, that's for doing this. Now, what if it's going the other way? What if I have this golf ball rotating that way? It's got Romo, it has Tony because it's rotating, and its omega happens to be clockwise now, doesn't it? That's a different omega or a different direction of an omega. It's clockwise now, right? So if I have that sucker rotating now clockwise, if it's going that way, then what I do is I take my right hand, I curl them in the direction that it is rotating, and my thumb, which is still perpendicular to my fingers, is pointing into, right? And if you're going into, that means in that orientation, L is a circle with an X, means into the page, right? And that is a negative L. So negative Z. Okay, this L out here, up there, was in the positive Z. And you just made another connection, didn't you? Remember we said counterclockwise is defined as positive for torques. Counterclockwise gives you positive Tony, doesn't it? Counterclockwise means the mo is out of the page, and you can get that by curling your fingers, and your thumb will point in the direction of the mo. All right, you can do the same thing down there. So now what we'll do is once again take a look at my record player, which you may or may not be able to tell that it is in fact rotating till I do that. So now that bottle cap again has Tony. It is moving L-lerly, isn't it? And so if I were to ask you what's the one direction that this item is moving, or that this item's momentum is, even though it's moving in what? It's an X, Y circle. Its momentum then is in the Z. It's in the direction of the post. It's perpendicular to itself. Now, is it a straight up or straight down, a straight into or out of the page? And again, what we'll do is we'll curl our fingers in the direction that this thing is moving, and my thumb is now pointing down. So this again is a clockwise rotation for that bottle cap, and that bottle cap then has negative mo. It's Tony, it's L, which you can call me L, right? You remember that? Then this is a negative L. Now, if I were to have it rotate the other direction, it would have a positive L, wouldn't it? Now, what I would also like you to remember is we talked about torques, okay? And a torque is a radius times a force, an R cross F. Remember when we talked about cross products, we said the order at which you multiply vectors doesn't change their values algebraically, but it will change their value directionally. So right now, this guy again is moving. It has momentum that way. If I apply a torque to this turntable, and I make it stop moving, then I'm going to have to apply a force perpendicular to this guy over here. I'm trying to make that arrow perpendicular. So if I apply a force right there, I'm stopping this guy, aren't I? Okay, so I'm just making this sucker stop. Now what I would like you to realize is I'm applying a force, which is this arrow, that is a certain distance or radius away, aren't I? I'm applying a force that is a radius away. And again, that white arrow is just a radius vector, a r hat. It's just like an I, a J, or a K. And can you tell that the arrow that I'm applying here to make it stop moving, right? Because you can see it's moving that way. If I want to stop it, I have to apply a force in that direction, right? So the way I can figure out the direction of the torque I'm applying is to take your, it's a different right hand rule. Take your right hand and point it in the direction of the R, curl them towards the F, R cross F, and you see how my thumb is pointing upwards? That should make sense. It's pointing upwards. I'm applying a positive torque to something that is rotating negatively, and I'm causing it to stop. So right now this has negative mo. So if I apply positive torque by doing that, put a force that way, I'm reducing the amount of Tony this has. It's going from negative down to 0 because I'm applying a positive torque. So if I do an R cross F, the torque is straight up. If I were to go the other way, like we said before, like right now, just to get this thing moving, it's not moving, right? If it's going to move, this pen cap needs to be pushed towards me in the direction of that yellow arrow, right? Boom. See, it just, as it moves on the turntable. Well, now what I have to do to say, well, what direction is the turntable applying a torque on the bottle cap? You do the R, and then you curl your fingers towards the F. So R cross F means it's gaining negative mo, okay? So that's a right-hand rule. There are two right-hand rules. One is always an R cross F if it's a torque, or an R cross omega, or an R cross V. Remember what we said also here. I'm going to stop that. We also said this. What if this pen cap is simply moving that way, just moving across the page, just, I don't know, doing one of those. It's mo, right? Linear mo is mv, okay? And if that's the case, boom. So if the momentum is this way, then it has momentum that is in the direction it's moving. Well, you remember what L is? It's I omega, right? So the direction of the L is the direction of the omega. But it is also M, remember what we said, M R V. And that R cross V, and then you multiply by the sine of the angle between them. But that's the other way to communicate it. So what that means is this velocity with a cross product R cross V can give you the L. So if this thing is moving linearly, like the car in the problem we talked about the other day, if this is a car, and I don't know, we'll say this red pen cap could be the flagpole at Turpin High School, right? And this car is moving that way. Well, the radius, the distance from the flagpole to the bottle cap is that. And if it's moving that way, then it has momentum upwards. So if this bottle cap is just moving in a straight line relative to that pen cap, it has Tony R cross V. Just like in I omega, if it were going in circles this way, we would say it's got momentum like yay, right? If it's going the other way, R cross V, that's a negative amount of mo, just like if it were going that way around it, okay? So it's called a right hand rule. It's in it's in RF or an r omega, or just the direction of the eye. All right, but anyway, right hand rule, yay physics.